Hello everyone, welcome to this presentation. My name is Frederick Mwema and please like my channel if you find this presentation useful. I want to present to you my work I presented in an international conference on engineering for sustainability world on 4th of July at Covenant University in Nigeria. I want to present to you the surface properties and mechanical properties of aluminium thin film prepared via RF magnetron sputtering. In this slide, I just want to give a background of the applications of aluminium thin films. Aluminium thin films have excellent reflectance, and therefore they find applications in curved or parabolic concentrators. They also find application in solar cookers. Also find application in spheric mirrors, since they can filter the infrared rays. Also, because of the good corrosion properties, they find applications in protecting surfaces, in microelectronics, in iPhone or phone covers, and in steel or metallic structures. More details about the applications of aluminium thin film can be found in our paper published in 2018 in Journal of Alloys and Compound. We also find it's used as backplates for solar cells to concentrate the solar power. They are also used as interconnects in semiconductors, where they act as the barrier between the wafer and the silicon. They also find applications in microelectronics as conductors. Most interestingly is their potential to be used as wearable devices or in smart textiles. Now, the biggest challenge in depositing aluminium thin film is the defect and the coverage. It is difficult to achieve a uniform film, and we have been able to do a lot of work on sputtering to just evaluate which properties based on the system, on the equipment we have, which combination of properties or parameters can give defect-free and more uniformly distributed film. We have done a detailed fractal analysis of defects such as ALOX, and you can find our paper published this year in 2019 in Applied Surface Science. So in this work, I want to present to you thin film deposited within the low substrate temperature between 40 and 100 degrees for a constant time of 2 hours, and the aluminium is 99.9% target used, and the system we are using consists of 2 targets and a substrate. Steel. So we'll use a FCM and AFM and radiation and microwave to characterize various properties. So welcome back. Saying we shall use FCM to do the surface microstructure, AFM to do the profiling, and nanoirradiation for mechanical, microwave for wear analysis. So our FCM results show that at 40 degrees Celsius, the microstructure consists of fine amorphous aluminium structures. There are also occasionally large and long structures appearing as bright features shown. But at 60, the structure appears highly porous with peaks of pores and long channels of porosity on its surface. However, increasing the temperature from 80 to 100, there is formation of larger and well-defined aluminium grains with fewer porous structures. These results can be attributed to the fact that increasing high temperature increases the atom energy atom energy on the surface of the substrate and hence enhancing grain growth. Our AFM profiling showed that the roughness generally increased with temperature, although there is a slight deviation at 80 degrees, and these results can be explained in terms of the grain growth and the porosity, which means that the values of high roughness may indicate either high porosity as shown at 60 degrees or very large grain sizes as shown at 100 degrees. The large error bars observed at 40 degrees Celsius are indications of non-uniform distribution of the surface structures, and as such, microstructure in this case is not homogeneous because it has large, it has pores and fine grain structures, and these results can further be confirmed by the FCM where we saw large and fine structures. The error bar at 100 degrees is insignificant on the roughness computation, which indicate that there is uniform distribution and growth of aluminium grains at higher sputtering temperature. We were able to do sputtering, fractal feature characterization at 100 degrees at different scaling, and we were able to see consistency in the fractal dimension, which means that 100 degrees give the better microstructure and surface profiling properties and a more uniform structure. In our mechanical characterization, the higher values obtained at 104 degrees, while the lower values obtained at 860 degrees. The highest modulus and hardness are obtained at well-defined and porosity-free microstructure at 100 degrees, while the high hardness obtained at 40 degrees can be attributed to fine structures observed in the FCM, such that if the denser hits on this region with high density of fine structures, we are likely to experience higher mechanical properties. The lower values at 60 degrees can be attributed to very porous structures and pits on the surface, such that if the intender hits on these pores, the microstructure will just collapse and it will sense a very low hardness. As such, we did microwear analysis for 3,000 seconds. The coefficient of friction against time is shown. We were able to get this average stable coefficient of friction for the 4 samples. It was found that the highest average of coefficient occurs at 100 degrees, which shows that these samples have the highest resistance to mechanical degradation or to wear. Also, the samples at 4 degrees had a higher resistance to sliding wear, and this could also be attributed to the fine microstructure, however, and higher hardness and the Young's modulus. However, we can conclude that 100 degrees presented better film quality because the microstructure was uniformly distributed, higher hardness and Young's modulus, and higher coefficient of friction was reported. and therefore this result gives a rough idea of industrial optimization of magnetron sputtering, especially considering the effect of the substrate temperature within the low substrate temperature range. Consider several references, and I will refer you to my article number 6, which you can go through. I will also refer you to article number 4, to be very useful, and article number 1 for your reference. Thank you very much, and you can contact me via this email in case you need further discussion. Thank you very much, and please like my channel.